attending this milestone in my life. As Dr. Taufer mentioned, today I will be presenting my contributions towards enabling reproducibility, scalability, and orchestration of scientific workflows in HPC and cloud-converged infrastructure. I want to start by acknowledging and thanking my advisor and the committee members for the critical role that they have played in the development of this dissertation. The contributions that I'm going to show throughout this presentation are the result of many collaborations with scientists across different institutions, to whom I'm deeply grateful for the support and the guidance. I also would like to acknowledge the GCLab members for their support throughout this journey. Now, as part of these collaborations, that have led to different research accomplishments, such as peer review conference and journal articles, posters and short papers, as well as open source software. And the list that I just presented of these research artifacts or accomplishments also support the contributions that I'm going to present next and the results. So let's dive in. Computational workflows have played a critical role in developing and accelerating scientific discovery. And this happens across different fields. We have worked directly with earth scientists, biologists, and material scientists. And we see that as we come together and collaborate to work and develop workflows, these workflows help into the advancements of applications such as drug development, wildfire detection and prediction, understanding on Earth surfaces for precision agriculture. And all these applications that I just mentioned are important for humanity. So this is the impact that scientific workflows have on us as a society. We see that as the sciences evolve and the technology also evolve, these workflows evolve and grow in complexity. So here we present a timeline of very well-known scientific workflows that have been orchestrated and use cases in Pegasus, that is a workflow management system. And we see how these workflows throughout time, grow in complexity. And what we see is that this complexity is exhibited, or we see some features or capacities of the workflows that exhibit this complexity. One of them is that most of these workflows are data-driven. And because they are data-driven, they require big data. This data is not only coming from one source. There are multiple sources, and all of them are streaming. There's also applications that transform the data in complex ways. So we have reductions from big data to small data. Or we have even expansions of data, how a model just generates tons of data. Another aspect is that within one workflow, we have heterogeneous code. Some of the applications might run on GPU and some others on CPU or even TPUs. The languages, the programming languages, even within one single workflow can be different. Another aspect is that the computational of these workflows is not always at the same place. We have distributed infrastructure. So for example, we see how workflows collect data at the edge and then they process it in the cloud. Finally, with the trend of artificial intelligence and machine learning, most of these workflows have been deploying these advanced computational techniques. However, as we know, these methodologies or these techniques have limited transparency. So with this list of features of the workflows, we can see how they exhibit this complexity. As this complexity increases in the workflows, we see that their robustness decreases. We define the robustness as the capacity for these workflows to be reproducible, to scale in performance, and to exhibit trustworthiness in terms of the data, the results, and the infrastructure. In the process of pursuing this robustness for the scientific workflows, we identified three main challenges that hinder that robustness. The first one is that because the workflows include many interoperable components like data and applications, they're hard to trace. And because they integrate artificial intelligence and machine learning models, they limit the transparency. And that leads to a lack of traceability, explainability that impacts the reproducibility of the workflow. A second challenge is that usually scientists are aware of the input data and can predict a little bit of the output data, but they don't understand the impact that can have the intermediate data that is hidden. And the infrastructure where these workflows are running can affect or reduce the scalability as they write and read this data. The third challenge is that also given the nature of some infrastructure, specifically storage infrastructure, the data can be ephemeral. That means that if the scientists cannot access the data because the infrastructure doesn't let them do it, how could they trust the results? How could they trust the data? And how could they trust the infrastructure? So these are the three challenges. We claim that to accelerate scientific discovery while ensuring robust sciences, domain and computational scientists need to come together and co-design scientific workflows in HPC and cloud-converged infrastructure to, one, support the traceability of data and applications, the workflow components, and be able to explain the results to therefore achieve the reproducibility. Second, to manage the infrastructure in a way that is going to be able to handle the intermediate data and therefore enable scalability. And the third one, orchestrate the data and the infrastructure to manage the data in a way that it can be persistent while still ensuring scalability, and that will enable the trustworthiness. To validate this statement, we contribute with 3 items. The first one is the creation of a fine-grained containerized environment that is going to enable traceability, explainability, and therefore reproducibility. We have the definition of a methodology that is going to help us manage the HPC and the cloud-converged infrastructure that will support the intermediate data and will enable scalability. And the third item is the design of a software architecture that is going to, during the end-to-end orchestration of our workflow, provide efficient data management, guaranteeing the persistency and also the scalability of the data. Because we have been working with different scientists across domains, we wanted to illustrate these challenges in a real workflow. Specifically, we worked together with scientists at the University of Delaware to develop SomosPy. SomosPy is a machine learning-based earth science workflow that has 4 different modules. And each of these modules generate, transform, and predict, and analyze and visualize topographic data. This topographic data can be terrain parameters or soil moisture. And one way that we could see, that I wanted to show you how this workflow works is that we use these terrain parameters and satellite soil moisture data that, as you can see here, is very coarse. It has a coarse resolution, so there are gaps. And we combine these 2 information, this data, topographic data, to fill in the gaps and predict higher resolution soil moisture using machine learning methods. This is not the only way that this workflow can be beneficial. Soil moisture can be beneficial for applications like precision agriculture, or even hydrologists can use this data for other applications, or wildfire detection. So what we see is that this workflow exhibits the 3 challenges that we presented, but we need this workflow to be robust so that the other scientists that are using this data can trust the results of the workflow. Let me tell you how this workflow exhibits all these 3 challenges. The first one is the lack of reproducibility. So workflows can be opaque, and that because they have summary components, they are hard to trace, and they use machine learning that limit the transparency. In this case, just to simplify a case of reproducibility, we see how by having one input data, scientists can obtain multiple results, and they might not understand why these results are happening. That's the first challenge. The second challenge is the lack of scalability. Scientists are aware usually of the input data, as I was mentioning, or the output data. However, they don't understand the impact of the intermediate data. So in this case, in this workflow, data can scale in different ways. One way is that we have a region of interest, but we increase the resolution. We go from a lower to a finer resolution. So we go from 90 meters to 10 meters. And as we go from these 90 meters, we have 1.42 gigabytes of intermediate data. But as we go into the 10-meter resolution, this data increases by 100. And also the time it takes to read and write this data increases by the same amount. So this is critical to understand how this intermediate data is also affecting the scalability of the workflow. Now, the last one is that given the nature of the infrastructure, the data will be forced to be ephemeral. And that means that scientists won't be able to access that data, and therefore they wouldn't be able to trust. So now that we have presented these three and illustrated these three challenges, I'm going to show the contributions for each of them. Starting by how do we enable reproducibility? There have been different efforts for enabling reproducibility. And it seems that the foundation across all of them is the use of or the providing provenance annotation. So we see examples like custom file systems or ad hoc packages or container technology, even workflow management systems that will provide this information. However, we select container technology because it will enable us to encapsulate the workflow without having to re-instrument. And because we have a standalone packages, they can be re-executable and portable across for other people, and other scientists will be able to reuse. However, there's one issue with container technology, and is the granularity. And I'm going to tell you how I address this. So let's go back to the problem of how can we reproduce if we cannot understand how we're getting these results? So we get from this workflow execution, we know that we're using machine learning models, but we don't know, what hyperparameters, what models we use. And automatically we want to understand, okay, what is A, what is B, what is C, what's the reasoning behind them? So with our contribution, we link the results to the applications to deepen the understanding of the data and the outcomes of the workflow. So in this case, we are able to track and to see that A, B, C come from different machine learning models, the first one being K nearest neighbors, and that we see these sharp edges of the soil moisture because we have neighboring information. So that makes these changes between the high and the low soil moisture values. Now, with random forest, we can get a better understanding because we have these tiles, these squares, because of the best split strategy that random forest uses. And with SBM, as we identified that this is the machine learning model that we're using, we see this soft or smooth surface because we're using polynomials to predict the soil moisture. So how do we automate this? How do we give this information to the scientists in an automatic way? We use container technologies. And as I mentioned earlier, there was one issue about the granularity, because containers tend to be coarse. But in this case, we're wrapping each data container and each application. The ones data is in blue, applications are in orange. And we see the DAG, the directed acyclic graph that follows this workflow. And we see that A, B, C are the three output containers, and that these are generated when we find the record trail that they're generated by each of these different models. And something that is important is that we not only capture, this is the model, but we also capture the parameters, the hyperparameters that have been used at the command line. Now, how do we create this fine-grained containerized environment? So we move from a native environment where there are no containers, no virtualizations, these applications and this data run on the bare metal machines, into a fine-grained workflow where we decouple and containerize each of the data and application components. We connect them through a zero-copy communication, so there is no redundancy in data. We develop a plugin that tracks and collect provenance information, and we annotate each of these components. So as you can see, there's metadata, provenance information for each of them. And to interact with this metadata, we have an interface where scientists can access this metadata and also interact with the workflow components. So the environment looks something like this. We have our data containers in blue that follow a file system in a file where we wrap our data. We have our application container where we have our scripts or executables, as well as the software stack. So that's going to be important because we're packaging the libraries and the specific versions in order to run that application. We have metadata that is, helps us identify each of these components. And this metadata is generated through a plugin that is going to interact with all of them. And finally, this metadata and the components can be accessed through a user interface. Now, I guess the next question that you might be asking is, okay, we are containerizing everything. What's the cost of that? And overhead is expected, because we have extra layers of virtualization. We know that and also the metadata management, we know that there's going to be overhead. However, empirically here, we wanted to provide guidance on what is this trade-off. So we test for the three models that I presented, k-nearest neighbors, random forest, and SPM, for the same region, Midwest, but at the top, we have a coarser resolution, 1 kilometer, so the input data is 38 megabytes. And for the bottom image, we have 90-meter resolution, so that is finer, so we have around 445 gigabytes of data. And what we see is that as the data increases, so as we go from the 1 kilometer to the 445 gigabytes of data, this overhead reduces. We are able to reach 12, 14, 13% of overhead compared to native, which is lower. And here again, what we want to point out is the trade-off between what scientists will get by tracing and explaining the results versus this performance. So this could be good for testing and getting workflows up until the production level. In summary, in this first contribution, our environment has different features that are going to enable the traceability, explainability, and reproducibility of scientific workflows. And we show that we have a low overhead in terms of time, and we also measure storage. Now let's move into the second contribution, where we enable scalability. So as I mentioned in the problem, data can grow. In this case, we grow from a coarser to a finer resolution, and the intermediate data impacts. But there's another case where data can grow also as we zoom out in a region. So we go from a state that is the Midwest around the Oklahoma state to the whole United States of America, having the same 10-meter resolution. And what we see is that the intermediate data reaches the terabytes as well as the input data, and as we write and read this intermediate data, or the data is going to have an impact in the scalability, so it's going to take more time for us to read. What we see is that part of that writing and reading depends on the infrastructure. So we wanted to check what's the state of the art of how infrastructure manages the scalability. So the first that we see is that traditionally scientific workflows, we have examples like montage, LIGO, epigenomics, run and were deployed on HPC resources, where they have, the optimized resources, the specific IO, and it's everything, dedicated resources for them. But we also see a trend of how the same workflows and how scientists using the same workflows have moved their workflows to the cloud because they can get more customizable or elastic configurations of their environments, of the computational environments. However, what we see is there is a missing work in designing HPC and cloud-converged infrastructure. We want to identify common technologies or common things across both of them. Now, in terms of the scalability studies, there are many for data-driven workflows, and they use, different storage technologies. However, they don't emphasize on the impact of the intermediate data and how by tuning, and specifically converged infrastructure, this can help the workflows. So with that in mind, we built a multi-layer infrastructure on top of Kubernetes. And what we have here is that we have our infrastructure in gray, and the blue is our storage. And we needed a storage that was able to support the distributed computation, because we're going to have parallel, applications, multiple users running this. So we need this storage technology to be distributed. And cloud object storage, or COS, is a technology that is going to enable us. Now, how do we connect this cloud object storage to our application? So that's when we take a look at the figure on the left, and let's take a perspective from an HPC in the cloud service. This is LSF, and what we wanted to see there is how legacy applications, that they usually speak in file system language, and if we connect them directly to this distributed cloud object storage, they wouldn't, we will have to re-instrument the code. So to address this, we want to support them using S3FS, this middle layer that is going to make the cloud object storage POSIX compliance. And we transfer this knowledge from HPC, we bring this perspective from this HPC as a service into the cloud native. And of course, we have to adapt other extra layers in order to work. But we can see how this transfer of knowledge let us also in Kubernetes, that is a cloud native service, run these legacy applications. Now, Kubernetes was an architecture meant to be for services, workflows. And we're talking now about scientific workflows. So the out-of-the-box parameters, we measure empirically what is the bandwidth that we're going to get by, writing and reading this data, this intermediate data. And what we see is that we get these values. However, we observe that this bandwidth can be improved. For example, the read can be improved by 28.4 and the write bandwidth can be improved by 1.5. That in the end is going to create an impact in the overall mix span of the workflow. Now, how do we do this? So because as I explained, the out-of-the-box settings, they come with a cost of passing the data. So we can tune the platform's I/O, specifically the parameters of the S3FS that are different parameters. And we perform an exhaustive search with different combinations using a benchmark, an FIO benchmark. And based on this exhaustive search, we can give best practices and provide an informed decision regarding what parameters to use. So as we see, the out-of-the-box were these 5 and 10 parameters, which gave us the lowest bandwidth. And then after tuning with the specific I operation, we get the highest bandwidth, and that's why we see the improvement. And it's important here that in this work, we also try to provide best practices or heuristics, but it's quite hard because what we notice is that the I/O can change depending on the I operation and the platform where you're running. Still, we gave as many best practices as we could. Now, after seeing when we tune, we see the impact after tuning, and we see the overall improvement of the make span by 8%. Of each of writing and reading for all these cases. And this can reduce hours of executing this workflow. Now, all this tuning was in a single node scenario. Now, what happens when we are actually running distributed workflows? And these workflows, because they're data-driven, they leverage data parallelism to compute faster the application. So in this case, we split the data, and each of these data tiles, are going to be processed by an independent compute unit. But the question here is okay, we already tune our storage, but how will it respond to multiple reading and writing requests at the same time? So to answer this question and to see the scalability impact, we practice a weak scaling. So that means that for 2 regions that are large regions, Midwest 10 meters and CONUS United States 10 meters, we increase from 8 nodes to 225 for Midwest 10 meters and from 8 to 152. And the problem size changes as we increase the nodes. So we're reading and writing more data. What we wanted to see here is that as we write more data, from more nodes, do we see any degradation in performance? And as you can see, yes, there's a variability as expected in the cloud. However, we do see, the performance maintains. The only sweet spot that we start, or spot where we start seeing decrease is for the read bandwidth. And that could be nice to explore as future work. Where is the point? But in this point, we're actually reading almost 800 gigabytes of data. So that's something that we could explore. Now, in summary, in this workflow, as we identify the impact of this hidden intermediate data, we can tune the infrastructure or build and tune the infrastructure that is going to enable that scalability. And we could reach accumulated bandwidths of 2.4 for read or 11.2 gigabytes per second for read. And then we can have a distributed of 225 virtual machines. Now let's move into the final contribution. This is about designing, enabling trustworthiness. So we're going to part from the same infrastructure as in chapter number 2, where we have our cloud native, Kubernetes, and OpenShift. And we see something new that is no local storage or local SSDs. Theoretically, these node local SSDs have better performance. They have higher IOPS, low latency. However, they have an ephemeral nature. So that's something that if data doesn't exist, if scientists cannot access, how they will be able to trust. So now let me show you step by step how we do this. So when we run cloud object storage, as we already proved it in demonstrated in chapter 2, or in contribution number 2, we see that object storage actually is able to handle the growth of data. In this case, we perform the first module of SumOfSpy, where we generate terrain parameters, and we go from Tennessee to the eastern US, so more data. And we see that the cost or cloud object storage is able to hold this performance. However, as we leverage node local storage, we reduce this workflow's make span up to 35%. So we see that the overall make span is reduced. So we can confirm that by using node local storage, the performance is better. That's good. However, there are two main issues with this ephemeral nature of the node local storage. The first one is the lack of persistency. That means that because the data is allocated within the node, let's say that if the node fails, or if the node gets in maintenance, or if the people loses access to that node, that data will be lost and scientists won't be able to access. The second aspect is the shareability. So let's say that the node is fine, nothing happens. And let's say that this part of the workflow, everything fits in node 1. But as soon as we reach these, the crop tile tasks that are like data parallelism, some of these tasks will be, or applications will be allocated at a different node. In this case, we see that this crop tile N is allocated in node 2. However, when this task is looking for that data, because the data is in node 2, there's no way to access that data, so then the workflow will fail. So these are the two issues that we see with persistency and shareability that we need to address to run the workflows. So we wanted to learn what's the related work, what's the state of the art. And we, because we're aiming to learn from all the infrastructure, we take HPC as a inspiration. So they use the node local, they have the same management between this intermediate or like a node local storage that is fast and the persistent storage that it will be a parallel file system. And basically what they do is that the application will write into node local storage. So it would be fast, it would be a fast writing. And then underneath, the burst buffers will be a combination of software and hardware that will make asynchronously the transfer of data from the intermediate and ephemeral node local storage to the persistent storage. And we see how this technology have been present at different supercomputers, being the last one, El Capitan, with the data rabbits. Now, understanding the HPC perspective, we want to see what's the perspective in the cloud. And we show solutions that are open source, so people could access, and enterprise, where people would have to pay. With open source, we highlight two. However, for Maestro, the main thing is that it doesn't directly offer the management between node and object. It will just select one of them for you. And the second technology, OpenEBS or Maestro, the main thing is that it will still have, this open source solution was developed for one cloud vendor. So there's still some locked with the specific vendor and some class of storage that will only run, and it will make it harder to run on other clouds. And the main thing about the enterprise is that these are solutions that because you'll have to pay, they like a little bit of transparency. You could have binaries of the Fusion file system, but then you don't have much understanding and it's just like high price. So for us, our goal was to create something that was open source and that it wouldn't create that lock with like a specific technology. So to do that, or a specific cloud vendor. So to do that, we designed a software architecture that leverages node local storage and ensures the persistency and the shareability of data while also enabling scalability. And to do this, we use Kubernetes. So Kubernetes and OpenShift, these cloud-native clusters, allow us that wherever you have Kubernetes, no matter which cloud you're running, our technology is going to run and it's going to be executed. Now, when we developed this architecture, we wanted to satisfy two requirements. From the application level, and from the system. So the requirements from the application is that we want to facilitate this for scientists. We don't want scientists submitting one task and one application at a time, and more when these workflows are so large. And from the system level, we want the data, our system to be able to handle the data from the node local and make it persistent to the persistent storage. So how do we do this? So we start by our baseline architecture, where we have our many nodes with the node local storage or local SSDs in gray. And we have our distributed COS or cloud object storage that it can be accessed across all nodes, but it's external. We have our API server that is going to enable the users or the scientists to connect with these resources. Now, the first part is the orchestration. So how do we orchestrate our workflows? We first model our workflows as direct acyclic graphs. So they, they're going to follow a flow. And we use kubeflow and Terraform to facilitates the infrastructure as a code. What does this mean? This means that scientists that have their applications in Python or another language, they won't have to touch that code, but they will just have to create a pipeline. And this pipeline in their own language, in a language that they're familiar with. And this kubeflow and Terraform will make the translation from the application, from that code into the specific infrastructure. So the scientists don't have to know about the resources, the Kubernetes resources. That's done for them. The second aspect is how do we persist the data? So to do that, we design a Kubernetes operator that asynchronously transfers the data from the node local storage to the persistent storage. And how this operator works is that it has a watch state where it's looking at the workflow pods. And as they follow the DAG, this operator will know when to transfer the data. And it will create these transfer pods that make asynchronously the transfer from the node storage to the external storage. Something that I want to highlight here that is important of this operator is that we cannot just do, transfers of data every now and then, because, for example, if we see this workflow here in this corner, this data cannot be transferred right immediately because if we see this other application is being used. So that's why the operator has to have a sense of when to transfer the data. We have to respect the flow of the workflow. Now, how do we share data? So for this, we use a network file system because it's widely used. And there are two main reasons. Is the simplicity and the accessibility by many, but many people use in the cloud. It's just simple and easy to set up. And also it enables us to have multiple nodes sharing the data. So it has a centralized place. We understand that, of course, NFS, even if it's a simpler solution, there could be some drawbacks, for example, the security or even part of the scalability at some point. So as future work, we would like to explore other technologies like BGFS, but that's part of future work. Now, with our architecture, we test again and we see, okay, yes, this architecture is letting us reduce the time by 35%, we are having the performance that we're expecting while still having the data persistent. Now, I think the next question, as always, is what's the cost? What's the cost of making this data persistent? So to this end, we quantify the overhead that the operator takes from, from when it finishes the workflow until it transfers all the data to the persistent storage. And we see that as the time of, as the data increases, as we have more complex applications, these data of transferring the data will increase. However, if we check even for this case, the time is 0.33% compared to the total time. So we could say that this cost of making the data persistent can be even negligible because we're having, the data persistent and still scalable. So in conclusion, with this architecture, we enable the end-to-end orchestration of our workflow with efficient data management. So we make the data persistent and shareable and still have the IO scalability. And we do this with even getting a 35% of increase. Now, as part of future work, there are two main things that I would like to do. The first one is to create a unified environment, so like a single entry point for all these features that we're enabling in my contribution. So it will be nice to have, a platform where people can access the provenance information, as well as the scalability features and the overall execution. So that's something we'd like to work on. And the second aspect is that we use SumOSPy to illustrate, and we also use some benchmarks, but it would be nice to stress our solutions by two aspects. The first one is evaluating advanced workflows such as LIGO, or the Laser Gravitational Wave Observatory, and MUMI, that these are very well-known applications. And the second aspect is that we could even try different cloud vendors to compare the performance trade-offs between them. In summary, we have enable scalability, that's something that scientists need. And we do it with a low overhead of like 10%. We also address the problem of writing and reading large intermediate data. And we do it by designing and building an infrastructure that ensures the proper management of that intermediate data. And then we also develop a software architecture that guarantees the data persistence and the shareability while having good performance or IO scalability for the workflows. And we even reduce the overall make span by 35%. I want to end up on a personal note and just thank everyone that have been with me throughout this process. It's been 6 years in grad school, so thank you to everyone. And thank you for attending this presentation. And I'm willing to take any questions or comments that you have. Thank you so much.